All right, let's go through a few examples of different types of chemical reactions just to show you. If there were, if we have something simple like this reaction, it's not balanced. We'll balance it later. Look at what type of reaction is this. It's good to let me write a couple more down to show you. Let's say all right, for these, Paul, you should hopefully know what types of reactions these are now. So we'll go through them first. Of course, this is a synthesis reaction. This will be decomposition. This reaction, we're producing carbon dioxide and water. I think in the list we had CO2, we had water first and CO2. It doesn't matter what order you list the products in. It's the same. We're producing them together. They're mixed together, so it's the same thing. So this is complete combustion. Now, of course, in this case, we're producing carbon monoxide instead, which we said you can still burn carbon monoxide. So this is going to be incomplete combustion. If we have something like NaCl plus fluorine produces NaF plus chlorine. Of course, this is going to be a single replacement reaction. Though if we had something like potassium hydroxide plus, say, aluminum sulfate, this would be a 2 and a 3. This will produce K2SO4 plus aluminum hydroxide. Of course, this is, as I said, double replacement. So we can use these reactions to predict products in many cases. Now, if I ask you to write the complete reaction for decomposition of ch3OH, then you would start something like, we're starting with decomposition of CH3OH. We'll produce the basic elements, carbon plus hydrogen, which we know should be H2, plus oxygen, which should be O2, since these are the diatomic elements. And that'll be the decomposition of, in this case, it's methanol. If we were to write the reaction for the synthesis of, well, let's do the same thing, CH3OH. Well, synthesizing, we're making it. So again, stress, pay attention to what the words mean. People mess these up because they try to memorize and aren't thinking about what the actual terms mean. If it decomposes, it's breaking apart. If we're synthesizing, we're combining something, we're creating something. So synthesis, we're producing CH3OH. And so we have carbon plus hydrogen plus oxygen will produce methanol. So then we have to balance the equation. So this is what we can do. You cannot do something like, or I could not ask you something like, what is the, sorry, kind of sloppy there, synthesis product of hydrogen and oxygen. You cannot predict that, so don't, kind of a sloppy H2 there, but because in this case, H2 plus O2, you probably might guess can produce water, but it can also produce hydrogen peroxide. So there are some cases it helps us predict, but we cannot predict everything. If I were to ask you to write the reaction for the complete combustion of, say, C2H4, what's that, ethene, then we know we're going to react C2H4, that is a hydrocarbon, contains hydrogen and carbon. And you should know the other product that we need is oxygen, so just keep that in mind. It's just common sense. People forget about it, but when you burn something, you need oxygen. You need to have a fuel and oxygen. You have a fire, you have a campfire, want to have a weenie roast, you have wood, and of course it needs oxygen to burn. So those are your reactants, and they produce water plus CO2 for complete combustion. So you can't predict the products. I'll only give you one reactant here, but you know the other reactant for combustion has to be oxygen. The ones that get people tripped up in many cases at first is the single replacement, double replacement reactions. Now remember, these are dealing with ionic compounds. So if we have something like, say, lithium oxide plus potassium chloride, and we want to figure out the products of this double replacement reaction, well, the cations trade places. That's all. But we need to make sure that the charges are balanced. So we write the ions first, like we normally do. So potassium oxide are our two ions, and it's just like you had potassium oxide, write the formula for it. We go through the same process. So potassium has a +1 charge, oxide has a -2 charge, so we need to have 2 potassiums for every 1 oxide, so it's K2O. Plus, we'll have, of course, lithium chloride. Lithium has a +1 charge, chloride -1 charge. Write down the formula. The subscripts in this case are 1 and 1, so that is our formula. Don't carry over subscripts like this in most cases, unless you're dealing with polyatomic ions. Remember that what this formula shows me is for every 2 lithium ions, I've got 1 oxide ion. For every 1 potassium, I've got 1 chloride. So you're taking 1 ion of each, combining them to figure out what is the neutral compound when those 2 ions combine. So again, that's why our subscripts don't carry over. So if we have something like, let's take just something simple, sodium chloride plus fluorine, we need to predict the products. Well, we'll produce a compound and an element. We need to decide what is going to react. Well, we need to figure out what type of ion does fluorine form. Well, it's group 17. It wants to gain an electron to get the noble gas configuration. Therefore, it's going to form an anion. We know it's going to be a -1 anion. Well, a -1 anion is not going to combine with a -1 anion or any negative anion. Negatives repel, so you will not have a nonmetal combining to form an anionic compound with another nonmetal. There'll be 2 anions. It's not going to work. So we have to have a cation combining with this new anion to get NaF. Again, don't carry over this Roman or this subscript. F2, that's because fluorine is a diatomic element. But when it forms an ion, it splits apart to form 2 -1 ions. So sodium's +1 ion, fluoride's -1 ion, so we get NaF. Plus the element that's formed, chlorine will form, elemental chlorine, and again, this is a diatomic element, so we get Cl2 being formed. Now if we had, on the other hand, NaCl reacting with, let's just say, aluminum, well, what's the aluminum going to replace? Aluminum forms a +3 ion, so it forms a cation, so it's going to replace the cation in this ionic compound. So our, I can find where my pen went to, there it is. Our ionic compound will be aluminum chloride. Look at the charges. If you're not sure, pause and write the formula for aluminum chloride. Aluminum has a +3 charge, chloride a -1 charge, so we need to have AlCl3 so that this compound is neutral. Plus, sodium is left behind. We need to form sodium metal for our product, and of course it's not diatomic, so it's just innate metal. These are simple examples. In later chemistry, we'll discuss which reactions are likely to happen. In this case, to be honest, sodium is a much more reactive metal than aluminum, so it'll probably go the opposite direction. But anyway, to show you how to deal with predicting products for ionic compounds, this is what we do. Just make sure that your final compound makes sense. Make sure that you're combining anions with cations in your compound so that your overall compounds are neutral. If you had something like calcium bromide plus, let's say, ammonium nitrate, these are polyatomic ions. Again, calcium bromide, this means for every one calcium ion we've got 2 bromide ions. It's not a bromine molecule. And this will produce, of course, cation switch places, calcium nitrate. You should know the charge of nitrate. You should be able to figure out the formula by now. Nitrate will be NO3 2 plus ammonium bromide. Oops. So we have a cation and an anion. Again, a cation and an anion. Make sure that your compounds are neutral. Common mistake people make is combining cations and cations to get 2 + 1 charges trying to combine. Doesn't work. And so again, ammonium ions have a +1 charge, bromide -1 charge, calcium +2, nitrate -1. So those are our formulas. And then we get to balancing, which is in the next section.